All right, so I assume in whatever chemistry class you had before, you did something involving acids and bases, probably. We're going to use some of those definitions that you've probably heard before, but also extend them in a way that makes more sense for organic molecules.
I'm sorry.
Yes?
So,
So there was a question about whether things were stereoisomers or conformers or constitutional isomers. Shoot, I think. No, was it 3?
I think it was.
It is 3. Oh, okay, so I still have those. Okay, so then never mind. Then I can take care of it. Sorry, I thought it was quiz 2, and I didn't have them anymore. All right, what was I going to say about acids? Oh, yeah. So in Gen Chem, when you talk about acids and bases, or whatever class you had before, when you talk about acids and bases, it was focused more on things like strong acids versus weak acids, dissociation in water, that kind of stuff. Organic acids are pretty much all weak acids, and so they are all weak acids. And so we focus more on the relative strength of the acids, and that's what we're going to look at today. So to do that, we need to make a couple definitions first. So this is probably something you've heard before, but if not, we'll go through it again. There's different ways of defining what's an acid and what's a base. And we're going to focus on 2 definitions in this class. The first one is the Bronsted-Lowry definition, where acids, does anybody remember what acids do in the Bronsted-Lowry definition? Acids are molecules that donate protons, right? So acids are molecules that can give up H+. That's what we mean by donate, just like they can lose H+. And in the Bronsted-Lowry definition, what do bases do? Accept, right. So this is different from the older Arrhenius definition of that acids produce hydronium in solution and bases produce hydroxide in solution. This is a more useful definition because we can talk about the hydrogens going somewhere or being taken or being given up. This also gives us a nice way to practice using our curved arrow convention to show what the electrons are doing. So when we let's look at an example of an acid-base reaction and how we explain that using these arrows. So we're going to look at acetic acid. All right, there's acetic acid. And then we're going to look at its reaction with ammonia. Okay, and here's some Lewis structures for acetic acid and ammonia. So now in a previous class, you might have looked at, transferring hydrogen, conjugate acid, conjugate base. Here we're going to be very specific in what exactly the electrons are doing when these 2 molecules react in an acid-base reaction. So we're going to say that well, which one do you think is the acid? It's a tough question, I know, but if you had to guess. Acetic acid, yes. So how does acetic acid fit in the definition? I mean, obviously it says acid in the name, but what is it going to do based on that definition, do you think? Yeah, it's going to donate that hydrogen, right? Okay, and so the ammonia is going to accept it, right? All right, but because we're going to be careful about this, we're going to think about how we describe this with the electrons and with the curved arrows. So we're not going to say that the hydrogen detaches from acetic acid and kind of floats over and sticks onto ammonia. We're going to say that the ammonia, the lone pair on the ammonia, grabs that hydrogen. Right, so the molecules come together, the ammonia grabs the hydrogen, and then the hydrogen detaches from the acetic acid. And when it detaches, the electrons that were making the OH bond go back onto the oxygen. So we draw like this. We say the arrows from the ammonia go out and, the electrons from the ammonia through the arrow go out and grab the hydrogen, and then it detaches and those electrons from the OH bond go back onto the oxygen. And then we draw the result of that. So the result of that is that now there is a third lone pair on the oxygen of acetic acid, which also means that it should now have a negative formal charge, -1 formal charge. And then the other thing that's present is now ammonium, ammonia with 4 hydrogens, and that's going to now have a positive formal charge. Good so far? All right. So now we can make another definition, what we call conjugate acids and bases. So acid-base reactions are reversible. So we're not going to be really like always looking from left to right. We want to look at the reaction as a whole that can go both ways. We want to make a conjugate acid-base pair. So in this case, the conjugate acid-base pair is the acetic acid and the acetate. We call that the conjugate acid is the acetic acid and the conjugate base is the acetate. So if you learned in a previous class that you start with an acid and then you make a conjugate base, that's not quite right in this kind of a situation. It's really, these things are conjugates of each other. Conjugate acid-base pairs will always differ by a hydrogen. Specifically a proton, H+. So what's the other conjugate acid-base pair in this reaction? Yeah, the ammonia and the ammonium. So there's another one here. As you can see, they differ by H+. All right. So acid and base as a definition, specifically in the Bronsted definition, this idea of donating and accepting, this is not an identity of a molecule. This is a description of behavior or of observed effect. So something like water can act as both an acid, it can give up one of its hydrogens, and a base, it can accept a hydrogen from somewhere else. So some molecules are only one or the other, but many molecules can either accept or donate depending on their circumstances. All right? And so the thing that we're going to really focus on here is the strength of the acid or the base, because the stronger the acid, the weaker the conjugate base. So a strong acid will have a weak conjugate base, and a weak acid will have a strong conjugate base. So for this to kind of make sense, we need to think about how we define acid and base strength. What do we mean? So does anybody remember, how did you define strong or weak acids in a previous class? What's the difference between a strong acid and a weak acid? Kind of. So it's how fully it dissociates in water. Because you could have a molecule with a whole bunch of hydrogens. That doesn't necessarily mean that it's going to dissociate more. But yes, that's the right idea. So a strong acid is one that fully dissociates in water, and weak acid is one that only partially dissociates in water. But in fact, there's a continuum. And some acids are going to dissociate more than others. So to measure that, we take something called a Ka, which you may have seen in a previous class, maybe not, but we're going to look at it here. So let's take, let's look at what happens when acetic acid dissolves in water. So there's our acetic acid again. In fact, just for practice, let's draw this out a little bit better. So we can draw that mechanism again. Okay, and we're going to react this with water. So in water, what can happen is the oxygen from the water can grab the hydrogen from the acetic acid, and the electrons go back like that. And we end up with an equilibrium. So we now have acetate ion and hydronium ion. And so the equilibrium constant of this reaction is what describes which side of the reaction is favored. So we can write a constant called the Ka, which is a ratio of the concentrations of some of the different species. So the Ka, and we're not going to do all the math on this. Did anybody do this in a previous chemistry class? Depends which one you took. Sometimes you did, sometimes you don't. But the Ka is going to be the ratio of concentrations between hydronium and acetate, so the stuff on the right side of the equation, divided by the stuff on the left side of the equation, but not water because that's a pure substance. So don't worry too much if you haven't done this before. It's not a big deal. I'll show you what we're going to actually do with this. So this is a constant, but if you look at the equation from like a math standpoint, you can see what's going on here. The more the reaction goes to the right, the more it produces the products, the bigger the Ka becomes. Do you see that? So the more let's imagine the reaction goes all the way to the right. So then the stuff on the right would be basically 1, and the stuff on the left would be basically 0, and so that number would be very, very large. And the opposite would make it very, very small. Now for all weak acids, except for those 6, HCl, right, HNO3, H2SO4, all the other weak acids, all the organic acids we're going to worry about, this number actually ends up being very small. All of these equilibriums are pushed more to the left. So the denominator is much bigger than the numerator in all of these cases. In fact, for acetic acid, this constant is, doesn't say. I can calculate it real quick here. Sorry, I thought it would say this, but let's try it. So this would be okay, so for acetic acid, this is 1.74 times 10 to the minus 5. And there's no units here because it's just a constant. So a very, very small number. So that means that the denominator here is much bigger than the numerator. And so that's called the Ka. So the stronger the acid, the bigger the Ka. Let's write that. Because as that acid gets stronger, it's going to push the reaction more to the right and make more hydronium in solution. So the bigger Ka for stronger acids, and the weaker acids will have lower Kas. But these numbers are a little unfriendly to work with. They're all these very, very, very small numbers with really negative exponents. So instead, much like with pH, we define a pKa as a log so that we can kind of bring these numbers back into a realm that's a little bit easier to deal with. So the pKa is defined as the negative log base 10 of the Ka. And so if we try this for this number that we just defined, we should get 4.76. If you remember from, I don't know, when did you do logs? Sixth grade, seventh grade math, something like that. If you remember back to that, logs give you the exponent. So the log of 10 to the 4th is 4. The log of 10 to the 5th is 5. The log of 10 to the minus 5 is minus 5. So these tell you the exponent, and of course you can always just put it in your calculator. We're not going to really calculate any pKa's in this class, but we are going to use tables of pKa's, and we're going to use them to help us judge other new molecules' pKa's. Because the pKa is a much nicer way of judging acid strength. So we can say, okay, acetic acid's got a pKa of 4.76. So do you think that a stronger acid will have a larger number or a smaller number for a pKa? So if we could find an acid that's stronger than acetic acid, is that pKa going to be smaller or bigger? Smaller, right, because it's going to be the inverse of the actual Ka. So a stronger acid will have a larger number for Ka, which will make a smaller number for the pKa because it says the negative. So a stronger acid will have a smaller pKa. Yeah, Kimmy.
Where did you get the numbers you have in the Ka? How did you get 1.8?
So actually, I thought they would have it in the book, but they didn't. So I used the pKa and went backwards. So like, if you take 4.76, that's the negative log of something. So if you go 10 to the negative 4.76, you should get 1.74 times 10 to the minus 5. You need to know the Ka, and then you take the negative log of that number to get the pKa. How do you find the? Oh, you have to look it up or something. Like it's an experimental value. Yeah. So you have to actually you can measure it. You can do an experiment and measure it, but you can't just figure it out from the structures or something. No. Yeah. Sorry. Yeah, what we'll mostly be using in this class is something like this. So we'll look at a PKA table, and we'll look up pKa's for various molecules. And this is a very simple one from the book with whatever 20 entries or so. You can look up extremely large PKA tables of all kinds of molecules. But ultimately, it's an experimental measurement. So if there's some new molecule, you can't look up the pKa. There's some software programs that can do an okay job of trying to calculate it based on orbitals and stuff. But mostly what we do is we look up pKa's of similar molecules, and then we try to figure out, is the molecule that we're interested in going to be higher or lower than whatever we just looked up on the table. All right, so take a look at some of these numbers. There's a couple to just kind of keep in mind that are useful. For instance, water. The pKa of water is about 16, just under 16. So would you say that water is a stronger or weaker acid than acetic acid? It's weaker, right? Because that number is quite a bit bigger. Also notice that this is a log scale. We used logs. So every one pKa value is really a 10 times difference. So the difference between acetic acid at 4.75 and water at 15.7 is a huge, huge, huge difference in acidity, which makes sense because we know acetic acid is like a pretty fairly strong acid, and water is definitely not. So as you go up from there, you get things that are extremely not acidic, like ethane. We talked about how alkanes are fairly unreactive. It's hard to pull those hydrogens off. It's hard to really do anything with them, and that shows here. You need an extremely, extremely strong base to be able to rip a hydrogen off of ethane because its pKa is way up at 51. And then conversely, if we go down and look at even smaller or even smaller numbers, some of our more like traditional strong acids, like we learned in Gen Chem or in previous classes, are actually down in the negatives because they're now so strong that they're creating actually fairly large values, Ka values that are greater than 1, which are going to give you negative pKa values. So you're going to look up a pKa in a pKa table, and then you can kind of use this to measure that. Probably the biggest difficulty here that people have, at least at first, is just keeping straight which number, like smaller versus larger numbers. So if something is a stronger acid, that pKa value is going to be smaller. And then the bases, it's just the opposite. The stronger base are the conjugate bases from very weak acids. So if you take something like ammonia and you deprotonate it, you take the hydrogen off of it, you've got NH2 minus, which is a very, very strong base. Right. Another thing that we're going to look at now is that we can use this idea of strength and weakness to think about stability structure-wise too. So what do you think is going to be a more stable structure? Something that is weak or something that is strong? Acid or base? What's more stable? Well, that's not really a clear question. Let me reword it a little bit. So let's take a look at, let's go back to our acetic acid structure versus water here. So if we're trying to judge the strength of an acid, is a more stable structure going to be a stronger acid, or is a more stable structure going to be a weaker acid? Weaker, right? Because if it's reactive, unstable, it's going to want to give out that hydrogen because it's not happy with the hydrogen as it is, so it's got to like get rid of it. So we can think about stability of structure as helping to figure that out. So let's take a look at the relationship between acidity and molecular structure. So can we look at a molecule and figure out, or can we look at two molecules and figure out which one's going to be stronger and which one's going to be weaker based on some criteria? And the answer is, yeah, a lot of the time you can. Okay. So our general technique here is to find the conjugate base and assess the stability of the negative formal charge. Now this isn't going to work for everything because some conjugate bases are neutral, some conjugate bases are 2 minus, whatever. But most of the things we're going to look at, most of the ones in that table, you have a neutral acid, you lose a hydrogen, and you end up with a negative formal charge somewhere. So we want to know what types of molecules can best stabilize that negative formal charge, and that's going to go back to our acid strength. Because we know that a more stable or a weaker conjugate base means a more acidic conjugate acid. So if we can look at this at the base and decide how well that negative charge is stabilized, we can take that information back and then be able to figure out which is the stronger acid. Okay, there's going to be a couple techniques that we look at. So the first one we're going to look at is electronegativity. Let's look at three potential acids. Here's three potential acids. They all have hydrogen. They can all lose their hydrogen and become a conjugate base. We want to know which one is the strongest acid. Now, just looking at those structures, I mean, eventually you'll be able to figure it out. You might be able to figure it out now just from previous experience. But the technique here is we want to look at the conjugate base and then think about that negative charge on the conjugate base. So let's imagine that each of these gets deprotonated. Each of these loses a hydrogen. What's the result? CH4 is going to become CH3 minus. NH3 is going to become NH2 minus. Let's keep track of our electrons too. And H2O is going to become hydroxide OH minus. So those are the conjugate bases of those three acids. Any questions on how I got that? Makes sense? Okay. So now we want to judge those three conjugate bases and decide which one can best stabilize that negative charge. So what do you think? Which of those three conjugate bases is happiest with a negative charge? OH. Correct. Why? Yeah, exactly. So the oxygen here is the most electronegative. So this is the weakest or most stable of the three bases. So then what does that tell us about the acids? What's the strongest? Right, so water is the strongest acid among the three acids because it has the weakest conjugate base. Okay. So if we were to rank acid strength, we would say methane is the weakest, then ammonia, and then water. And we can actually then check that by looking it up in the table. So let me rewrite these over here. So CH4, NH3, and H2O. If we go back and look up those pKa's, CH4, okay, it's not exactly in the table, but it's probably pretty close to the CH3. There might be a bigger table in the back here somewhere. Maybe. Yeah, so we'll say it's about 50 something. Probably bigger than ethane even. And then ammonia is 38 and water is 15.7. Okay, so our guess was right. We checked it, and yes, water is the strongest acid, then ammonia, then methane in that group. And that's because of electronegativity. Okay. Now we have to be a little bit careful with this rule. It's a nice, simple rule, but it only works in the same period. or row of the periodic table. And that's because the size effect of dropping a row or two rows ends up being more important than the electronegativity effect. So if we're comparing like chlorine and iodine or something like that, which we're going to do in a minute, this no longer really holds. You can't look at electronegativity that way, only for the same period. So let's look at that one next. So another effect on stability of a negative charge, actually the next couple that we're going to look at, is how well can the negative charge in that conjugate base be delocalized, be spread out. A negative charge that's very, very concentrated in one little spot is much less stable than a negative charge that's spread out over a large area, which kind of makes intuitive sense. If you spread out the charge, it's more stable. So there's a couple ways we're going to look at what we call spreading out the charge. And the first is the simplest, just the size. If you have a negative charge in here, in this kind of a sphere, versus a negative charge in this kind of a sphere, the charge density, the charge at any given point, is going to be much lower in the larger ones. We would say this one has a lower charge density and is therefore more stable. So how this works in an actual example is that if we looked at like the acids of some of the halogens, like let's look at HI versus HF. So according to the electronegativity rule, we would expect that F is more stable as a negative charge, because again the conjugate bases would be I minus and F minus. And we'd say, oh, F is more electronegative, it's more able to stabilize its charge, so HF must be the stronger acid. But that's not true because I is so much bigger. I is much, much larger, and that makes it a weaker base. And so HI actually ends up being a stronger acid than HF. Because of that. And so that's going to be true throughout the periodic table. So like O versus S and so on, and Cl and Br, wherever you find that kind of thing. It's not, I mean, we're not going to deal with the metals and stuff, but pretty much over in the nonmetals, we're going to see that. I don't love the PKA table in the book is not great either, so I'll post one that's a little bit more complete, and at least for the next couple exams, you'll have a PKA table to use on the exam as a reference. All right, the next one is the resonance effect. So how does resonance affect the pKa if that charge can be moved around or not? So let's look at a couple similar structures for an example. So we're going to stick with our acetic acid. And we're going to compare it to ethanol. Okay, so acetic acid and ethanol, which one is the stronger acid? Now you can probably figure out it's going to be acetic acid because it has the term acid in its name, but that's not a great reason. So let's look at what's really going on structurally where we can figure this out. So once again, we want to look at the conjugate bases of both of these. conjugate base of acetic acid is acetate ion, and the conjugate base of ethanol is called ethoxide. Okay. So based on, whoops, I forgot some lone pairs here. Based on what we've talked about so far, it would appear that these are essentially equal. They both have an oxygen atom with the negative charge, so same kind of atom. So the two previous things we talked about don't have any weight here. But one of these is definitely a stronger acid than the other. And the reason is because of resonance. So remember a few chapters ago we talked about writing some resonance structures. So we can write a resonance structure for acetate ion that looks like this. And remember that resonance structures don't flip back and forth like that in real life. They're actually an average. The overall structure is an average of all the resonance forms. So we would say that the actual structure is a hybrid of these. That's always a little bit hard to draw, but we might express it something like this. Where each of those carbon-oxygen bonds is kind of like 1.5 bonds. And the effect of that is to delocalize or spread out that negative charge. So now we would say that negative charge is not just stuck on one oxygen, it's actually shared between two oxygens. So each oxygen really only has like a half of a negative charge on it. And that's a much more stable situation. So this anion is, we would say, resonance stabilized, which means that the effect of that resonance is to stabilize that charge and stabilize that overall structure. So this charge, or this base, where the negative charge has resonance there, is then more stable, weaker base, and therefore its acid is going to be much stronger. So if we look at those actual pKa's, the pKa of acetic acid, we already talked about, is 4.76. The pKa of ethanol is similar to water at 15.9. So the acetic acid is much stronger base, can lose its hydrogen much more easily than ethanol can because of the resonance effect there. So that's relatively straightforward here, but that's also the case even when the resonance forms aren't quite as good, meaning like it's not an even sharing between them. So let's look at another example. Let's look at cyclohexanol, which is an alcohol. Versus phenol, where that ring is called benzene when it has the alternating double bonds, and cyclohexanol doesn't have those alternating double bonds. It's all sp3 hybridized carbons. So all sp2 carbons in phenol versus all sp3 carbons in cyclohexanol. And actually, do I not have this in here? Yeah, we definitely need a better PKA table. This is frustrating. Okay, well, it's close enough. All right, so cyclohexanol has a PKA around 16. And phenol has a pKa around 10. So which is the stronger acid? Phenol. Why? What?
Like, it has lower PKA.
Yes, it has lower pKa, but why does it have a lower pKa?
Is it because of the double bond?
It is, but what are they doing? Why? Any idea?
The double bond?
It is the double bonds, so why? What are those double bonds doing? They are stabilizing it. Any idea why? How? So here's how we would explain this. Once again, we're going to look at the conjugate base. Conjugate base of cyclohexanol is this one. Conjugate base of phenol would look like this. So the cyclohexanol, that charge is stuck. It is isolated, it is localized on the oxygen. Phenol, it is mostly on the oxygen, but there are actually resonance forms we can draw that show the negative charge going elsewhere. So for instance, we could draw a resonance form like this. That actually moves that negative charge over to the carbon. We can keep going, and we can move it to this carbon. And then there's actually a third resonance form where we can pass it over to this carbon as well. Now, if we're judging resonance forms, like which ones are better, we don't usually put negative charges on carbon. We don't think of that as like a stable situation, really, because we know that carbon-hydrogen bonds have a pretty high pKa. But they do contribute. There still is that resonance going on. It's not evenly weighted, but it's still happening. So that means that that negative charge on the oxygen is delocalized a little bit. It's brought in a little bit away from that oxygen and distributed around the ring with those carbons, and that makes that conjugate base a little bit more stable than it would be otherwise. Now look at the difference between that and acetic acid. Acetic acid had resonance too, but acetic acid's resonance was very, very stabilizing because we had two oxygens to share the negative charge between. Phenol's resonance is only a little bit stabilizing because we know that negative charges on carbon aren't really great. So that only contributes a little bit. But it's enough to make phenol more acidic than cyclohexanol because of that little bit of stabilization. So questions about that? Okay. So remember, we're always looking for, are there ways we can spread out the negative charge, or is it really stuck on one atom? And we're always looking at the conjugate base to do that, to make that judgment. Okay, the last, right, we're on 4, I think. The last one we're going to look at here, 4. The last effect is called the inductive effect. The inductive effect is when electronegative atoms we can think of it as electronegative atoms pulling the negative charge toward them, creating a delocalization effect. So let's look at an example. We'll look at acetic acid again, but this time we're going to draw the whole thing out. Okay, so there's our acetic acid again. And now we're going to compare it to trifluoroacetic acid, which is this. So this time, same exact molecule where the acid part is concerned, but it's actually way over on the carbon on the left that we're having a difference now, where we're adding some fluorine. If we look at the conjugate bases of these, they're going to look pretty similar. So in both cases, we've got a negative charge and an oxygen, so the same type of atom. We have the same resonance delocalization in both of them. The only thing that's different is those fluorines on the carbon. And so here's the effect. Our pKa, again, of acetic acid is 4.76. The pKa of trifluoroacetic acid is 0.23, much more acidic. So, now that we've had a little bit of practice thinking about these ideas, how can you explain that difference in acidity? How do you explain why trifluoroacetic acid has such a lower pKa than acetic acid? You want to give it a try?
I don't know, I just assume because it doesn't have the nitrogen.
It doesn't. It has fluorine instead. So what are they doing? It's not the size. It's something else. What else is special about fluorine? Yeah, so what would maybe fluorine be doing because of its electronegativity? Yeah, exactly. It's pulling the electrons. So even though we can't really draw it in a nice way like we would with resonance, we can still kind of say that this negative charge is kind of being generally pulled toward the fluorines because the fluorines are very electronegative. So the fluorines are helping to spread that charge out a little bit, even though we can't draw nice resonance structures that says the charge is shared between here and here and here and here. But if you remember, molecules aren't nice like that anyway. Molecules are just blobs. So if you've got the blob and there's a bunch of electronegative stuff on this side of the blob, then the negative charge is over here. That electronegative stuff can maybe pull that this way a little bit. And so that's called the inductive effect. And that's another thing that stabilizes the negative charge on a conjugate base. Questions about that? So this is a lot, but the good news is that these 4 effects that we talk about here with respect to acids and bases are basically how we explain all the reactivity for the rest of the semester. If you can evaluate stabilization of charge by resonance, by the inductive effect, by electronegativity, by size, then you're pretty much set for a whole lot of other stuff that we're going to be doing. So these are the 4 main things that influence the reactivity of organic molecules. And once you get good at evaluating them, you'll be able to answer a lot of questions as we go on in the course with pretty much everything else that we see. All right, so the last thing we're going to do about acids and bases is talk about another definition, a different definition of acids and bases called the Lewis definition. Now, the Lewis definition is often less convenient when we're talking about molecules that we define as acids and bases, like the ones that we just did before. But the Lewis definition actually expands the definition of acids and bases so that we can essentially explain every chemical interaction and reaction in terms of acids and bases, which is again why all those effects are so useful to know. So a Lewis acid is defined as an electron acceptor and a Lewis base is defined as an electron donor. So instead of dealing with H's now, we're talking about electrons. And because we're talking about electrons donating and accepting electrons, we're talking about making new bonds, making chemical bonds. So this has a lot more applicability to other types of reactivity. All right, so the general kind of idea of this is you have some molecule A, and then you have some molecule B that has a lone pair. That's your donor. So we say A is the acceptor and B is the donor. B, we draw a curved arrow saying that the electrons on B are going to A. And the result of that is that A is now going to have a little bit extra electrons, so it's probably going to have a negative charge, and B is going to have a positive charge. If we started with two charged species, then when they made the connection, they would become neutral. So let's see how this applies to our regular acid-base stuff, and then we'll look at an example to finish up that's a little bit different. So in a standard acid-base type reaction, we can explain this if we look at water reacting with a typical acid like HCl, hydrochloric acid. So we would draw this. We would say, okay, water is the base, HCl is the acid because water has the higher pKa. And that means the electrons from water are going to grab the hydrogen. The electrons from that bond go back onto chlorine. And then the result of that is to make hydronium ion and chloride ion. So in this case, water is acting as the base because it's accepting hydrogen, but it's also acting as a Lewis base because it's donating electrons. Its electrons are going out and grabbing something, and that makes it a Lewis base. So where this is going to be a little bit different is when we have reactions that don't involve the transfer of hydrogen. We can still talk about those reactions in terms of acids and bases, which means we can still use all those factors to evaluate whether something is likely to happen or what's more stable. So here's a reaction that we're going to see later on in the semester. We're going to have a molecule like this. Actually, I'm going to draw it a little bit differently, where carbon actually is missing a bond and has a positive formal charge. And we call that a carbocation. We can take our same water. If there's water in this reaction, if there's water around in that mixture, based on Lewis acid-base theory, what do you think might happen? Which molecule is best equipped right now to be an electron donor? It's the water, because you see it has the lone pairs. So which molecule can then be an acceptor of electrons? The other one. Why? Why would it be an acceptor of electrons? Yeah, the carbon's positive charge. It's electron poor. It's missing electrons. Carbon wants 4 bonds. So we would say that carbocation is missing electrons. So we need to give it some. So in this situation, what happens, we would predict that the Lewis base, the water, the electrons, would attack the carbocation to, make that situation a little bit better. And that's exactly what actually happens. So then we have that kind of a product, and then actually there would be another step where a base comes along and takes the hydrogen off of one of those extra hydrogens off, and then we've made an alcohol. We've made an OH attached to that carbon. So this is the idea of the Lewis acid-base theory, is it doesn't have to involve the transfer of a hydrogen. If we have electrons, the electrons on one species are going to attack or connect with or donate, however you want to say that, the other species, and that's how we're going to make these bonds. And this idea explains pretty much everything we're going to do the rest of the semester. So it's a really good basis for all that. All right, any questions? Okay. If you have those, or no, I have the quiz 3. So I will finish up quiz 3s and make sure you get the extra points for that. You got all your notebooks. Lab Wednesday. I think that's it. Any other questions? Okay, I'll see you Wednesday morning. Hey, what's up?
Is it possible to make a phone, like, just not make a phone and kind of like ask a question after this class?
Yep,
Okay.
I'll be there.
Should I wait until after this?
Yep, I'll be right over there when I'm